These are your notes for Unit 9, Day 5 of Pre-Calculus. If you would like to see your warm-up, review question, or any homework questions we covered in class today, just look at your finished notes. So today we are going to talk about how to use vectors to model some real-world problems. We will be able to find the dot product of two vectors. We will be able to find the angle between two vectors, and we will be able to figure out if two vectors are parallel or orthogonal. And orthogonal is the word that we use for perpendicular for vectors. So modeling with vectors. So let's say we have an airplane, a Boeing 767 aircraft, that is maintaining a constant speed of 500 miles per hour headed due south. The jet stream, so the air speed, is 80 miles per hour in the northeasterly direction. Express the velocity sub A of the airplane relative to the air and the velocity of the jet stream, so the wind, in terms of both I and J. Then we're going to find the velocity, so we're going to find the speed of the airplane relative to the ground, and then we're going to find the actual speed and direction of the airplane relative to the ground. All right, so we've got an airplane, and it's traveling due south, so northeast, southwest. So we've got an airplane, and it's traveling due south. And so that is going to be our vector for our airplane, and that is going to be our J vector. And since it's traveling south and its speed is 500 miles, it's going to be negative 500. And then our our wind speed is going in the northeasterly direction. And so that is the vector for our wind speed. And it's 80 miles per hour. So the magnitude of this is going to be 80. It's going to be 80. And I guess I should just do this in terms of the magnitude. So the magnitude of the airplane is going to be 500. And notice this is vector I. So I would go in this direction. So in terms of I, the angle of the wind is in the northeasterly direction. So we'll call that angle 45. So the angle for our vector W is 45. And we can say the angle for our airplane, we can call that 270, or we can call it 90 or 0, whatever we want to call it. And then we have our wind is going to be 80. And then parentheses, so remember our vectors are the magnitude times cosine theta I plus sine theta J. And so that's how we determine our vector. So it's going to be 80 times the cosine of 45I plus sine 45J. And then for our airplane, we're going to have 500 times the cosine of 270I plus the sine of 270J. And if we want to find the speed of like the actual direction of the airplane, we're going to find this guy right here. And that would be vector A plus W. And so we're going to add those two vectors together. So A plus W is going to equal, well, if I figure this out, this would be 80 times square root 2 over 2I plus square root 2 over 2J, because the sine of 45 and the cosine of 45 are both square root 2 over 2. And for this, it would be 500 and then 0I and then minus 1J. And so if we multiplied this out, we would get 40 square root 2I plus 40 square root 2J. And then this one would be 0 and then negative 500J. So if you added these two vectors together, that would give you the actual direction and speed of the airplane. So if I added those, I would get 40 square root 2I plus 40 square root 2 minus 500J. And then if we found the actual magnitude of that, Remember, to find the magnitude of a vector, you take the square root of a squared plus b squared. And so this is going to be the square root of 40 square root 2 squared plus 40 square root 2 minus 500 squared. And so if we did some calculations here, we're going to do the square root of 40 square root 2 squared plus 40 square root 2 minus 500 squared. And so the speed of the airplane relative to the ground is going to be 447 miles per hour. And then if we wanted to find the angle created, remember the tangent of our angle is b over a. So in this case, it's going to be the tangent of theta is going to equal 40 square root 2 minus 500 over 40 square root 2. And so if we did this, we would get, we'll inverse tangent both sides to figure out theta. So we'll take the inverse tangent of both sides. So I'll do this all in one step. So we're going to do the inverse tangent of 40 square root 2 minus 500 and then divide, and then divided by, and divided by 40 square root 2. And so, I'm in radians, let's switch to degrees. That would be, theta is going to be negative 82.73 degrees. So what does that mean? That means that from our vector I rotated down in this direction negative 82.7 degrees. But remember, when we're talking about airplanes, we talk about its angle relative to the north or south direction. So if I rotated negative 82.7 degrees, then the amount of degrees that it's rotated up from south would be 7.3 degrees. So my airplane is traveling in 7.3 degrees east of south. And so that would be the angle or the direction of my airplane relative to the ground, and then it's traveling at 447 miles per hour relative to the ground. Two movers require a force of magnitude 300 pounds to push a piano up a ramp inclined at an angle of 20 degrees from the horizontal. How much does the piano weigh? All right, so here's our little diagram. So we've got movers, and they're pushing this piano up the ramp with a force of 300 pounds. So the magnitude of their force, so the force of the worker's magnitude is going to be 300. All right. And then the weight of the piano is exerting a force straight down. And so we can call that the force of gravity, or that's going to be the weight of the piano. And so the magnitude of F1 is going to be the weight of our piano. And then we've got this guy right here. Well, that doesn't make as much sense because the piano is sitting at an incline. So what we can do is we can draw a different triangle. So we still have the force of that piano coming straight down, which would be its weight. And then what we're going to do is we're going to take the force that the workers are pushing up the piano, and we're going to bring it down right here. And we're going to draw that right there. And we're going to call that F2. So the F2 is going to be the force of the workers pushing the piano up the ramp, and we'll call that 300. And then our last vector is going to make a little bit more sense. So that is going to be the force of the piano against the ramp. So the piano is sitting at an angle against the ramp, so its force of that piano is going to be at an angle. And that angle that's created between the weight of the piano and the force of the piano against the ramp is going to be 20 degrees because those two triangles are going to be similar. And so now we have a right triangle. And so if I were to label the sides of the right triangle, the weight of the piano, or the force 1, is going to be the hypotenuse. F2 is opposite that 20-degree angle. and then F3 is going to be adjacent. Well, I'm trying to figure out F1. I want to know the hypotenuse, and I know the opposite. Well, to figure that out, I can use SOHCAHTOA. So the sine of angle 20 is going to equal the opposite, and the opposite is 300, and then divided by the hypotenuse, which is F1, and that's what I'm trying to figure out. I'm trying to figure out the weight of the piano. So to solve for F1, we're going to multiply both sides by the magnitude of F1 and then divide by sine 20. So the magnitude of F1, or the weight of the piano, is going to be 300 divided by the sine of 20 degrees. And so if I go on Desmos and do this, I would have 300 divided by the sine of 20 degrees, and the weight of the piano is going to be about 877.14 pounds. So that is another way that we can look at and use vectors to help us solve real-world problems. Let's look at another problem. A box of supplies that weighs 1,200 pounds is suspended by 2 cables attached to the ceiling as shown in the figure below. What are the tensions in the 2 cables? All right, so we're trying to figure out the tension in this cable. So what is the tension in that cable? We can call that force 1 or vector 1. And we're trying to figure out what the tension is in this cable right here. So we can call that force 2 or vector 2. And so we're trying to figure out the magnitude of those 2 forces. Well, we know that there's a third force acting, and that's the weight. So that's going to come straight down. And that is going to be, we'll call that force 3 or vector 3. And we know that the magnitude of that is going to be the weight, which is going to be 1,200. And so if I were to draw this on a coordinate plane, we've got our 3 vectors. So we've got vector 3, or we'll call that force 3, and we know that the magnitude of that is 1,200, and I know that the angle would be 270. And then we've got force 1, or vector 1, and it's coming up here. And so that's going to be force 1, and we don't know the magnitude of that force, but we do know the angle coming up is going to be 45. So we know the angle of that force is 45. And then we've got our third force, which we called force 2, is over here. And we don't know the magnitude of that, but we know that its angle went all the way over, and they told us that this little angle down here was 30. So that means that that big angle for force 2 is going to be 150. So the theta for force 2 is going to be 150. So now let's write those forces in component form. So force 1 is going to equal the magnitude of force 1 times the cosine of its angle, 45i, plus the sine of its angle, 45j. And so if I did this out, we would have the magnitude of its force times square root 2 over 2i plus square root 2 over 2j. And then our force 2 would equal the magnitude of force 2 times the cosine of 150i plus the sine of 150j. So that would equal the magnitude of force 2, which also would be the tension in the cable, times cosine at 150 is negative square root 3 over 2i, and then sine at 150 is 1/2, and then j. And then force 3 would be the straight coming down, so the force of gravity of our box, and we know that that's 1,200, and then it would be the cosine of 270i plus the sine of 270j, which would be 1,200 times 0, and then minus 1j. And so if I multiplied these out, I would get square root 2 over 2 times the magnitude of force 1i plus square root 2 over 2 times the magnitude of force 1j. And then this would be negative square root 3 over 2 times the magnitude of force 2i plus 1/2 times the magnitude of force 2j. And then we would get 0 minus 1,200j if I multiplied those out. Well, now we've got 3 different vectors. What do we know about those 3 vectors? Well, we know that that box is being suspended, meaning that it's not moving. Since the box is stationary or static, that means that the sum of those three forces is going to be 0 because none of the forces is winning. They all kind of tie. So if I add up those three forces, force 1 plus force 2 plus force 3, I get 0 because the box is stationary. It's not moving. So let's add up those three forces. So force 1 plus force 2 plus force 3. I would get square root 2 over 2 magnitude of F1 minus square root 3 over 2 magnitude of F2, and then I. And then we would get square root 2 over 2 magnitude of F1 plus 1/2 magnitude of F2 minus 1200 J. And we know that those two pieces are both going to equal 0 because if I add up those three forces, I get 0. So now I'm going to get a system of equations that would help me solve for F1 and F2. So let's solve that first one. So square root 2 over 2 magnitude of F1 minus square root 3 over 2 magnitude of F2 is going to equal 0. And so let's just solve that for the magnitude of F1. So square root 2 over 2 magnitude of F1 equals square root 3 over 2 magnitude of F2, and then multiply both sides by the reciprocal. And so we're going to multiply by by 2 over square root 2. And so those 2's would cancel. And so the magnitude of F1, or the tension in that first rope, is going to be square root 3 over square root 2 times the magnitude of force 2. So I'm going to use that eventually, but for right now, we're going to put a pin in it. And now let's go to our second equation. So we know if we take square root 2 over 2 magnitude of F1 plus 1/2 times the magnitude of F2 minus 1200, I should get 0. Well, now I'm going to take this expression and I'm going to substitute it in for the magnitude of F1. So now I get square root 2 over 2 times square root 3 over square root 2 magnitude of F1 plus 1/2, sorry, that's F2, not F1, magnitude of F2 minus 1200 equals 0. So now those square root 2's are going to cancel. So now I have square root 3 over 2 magnitude of F2 plus 1/2 magnitude of F2 equals, add that 1200 over. And so combine like terms, I get square root 3 plus 1 over 2 times the magnitude of F2 equals 1200. Well, to solve for the magnitude of F1, or that tension in that second rope, I'm just going to multiply by the reciprocal. And so the magnitude, or the force of that tension, is going to be, we're going to take 1200 times 2, and then divide it by square root 3 plus, get out of the square root 3 plus 1. And so the tension of force 2, or the tension in that second rope, is going to be 878.46 pounds. And so that is going to be the force exerted on that second rope. And then if we want to find the force exerted on the first rope, we're going to use square root 3 over square root 2 times the magnitude of F2. So we're going to take that, and we are going to multiply it by the square root of 3. And then we're going to divide that whole thing by the square root of 2. Oops. And so the tension in the first rope is going to be 1,075.89 pounds. And so those are the two forces being exerted on those two ropes. So the tension in that first rope, so the pink rope, is going to be 1,075.89 pounds. And the tension in that second rope is going to be 878.46 pounds. And so those are some examples of how we can use vectors in real-world problems. All right, so moving on to a new topic, the dot product. So the dot product is not necessarily multiplying two vectors, but we call it the dot product. So if you want to find the dot product of two vectors, it's kind of similar to matrix multiplication. I don't know if you guys remember matrix multiplication, but what we're going to do, if you want to find the dot product of two vectors, you take their two A components and you multiply them. And then you take their two B components and you multiply them, and you add the result, and that is called the dot product. So if we have two vectors, v and j, notice the a component for vector v is 2, and the b component is -3. For vector w, the a component is 5, and the b component is 3. So if I wanted to find the dot product v times w, I would take 2 times 5 plus -3 times 3. So this would be 10 minus 9, which is 1. So notice when we do a dot product, we get a number, one number, as an answer. If we want to do the dot product of w times v, we would take 5 times 2 plus 3 times -3, which would be 10 minus 9, which would also be 1. So notice the dot product of v times w is the same as the w times v. Let's find the dot product of v and v. So that we would do 2 times 2 plus -3 times -3, which would be 4 plus 9, which is 13. Or if we wanted to do the dot product of w and w, we would get 5 times 5 plus 3 times 3, which would be 25 plus 9, so 34. If we wanted to find the magnitude of vector v, so remember magnitude is you take the square root of the a component squared plus the b component squared. And so this would be 4 plus 9 square rooted. So the magnitude of vector v is the square root of 13. And the magnitude of vector w would be the square root of 5 squared plus 3 squared, which would be the square root of 25 plus 9. So it would be the square root of 34. Now, what do you notice? The magnitude of the vector is the same thing as the square root of the dot product. So that's another pattern or relationship that you can keep in mind. So that is called the dot product. If you want to find the angle between two vectors if they don't form a right triangle like we were doing before, well, remember with right triangles, you get to use the tangent of your angle. So if you're in I component and j component form, the tangent of your angle is the b over the a. But if you're not in that form, so if you have two vectors that are not in I and j form, they're out in space, then you get to use what you would do from the law of cosine. So if you remember, the law of cosines is a squared equals b squared plus c squared minus 2bc times the cosine of angle A. Well, if you solved for angle A, you would do a squared minus b squared minus c squared divided by -2bc would be the cosine of that angle. Well, that ends up being the dot product of the two pieces over the magnitude of the two pieces. And so if we did this, the cosine of this angle, you would take the dot product of the two vectors that you're talking about, and then you would divide by the magnitude of each angle underneath. So if we wanted to find the angle in between vector u, which is 4i minus 3j, and vector v, which is 2i plus 5j, we would do their dot product. So we would do the dot product of u times v and then divided by the magnitude of both of those angles. So we would do 4 times 2 plus -3 times 5 all over. The magnitude of u would be the square root of 4 squared plus -3 squared, and then times the magnitude of vector v, which would be 2 squared plus 5 squared. And so this is going to be, the cosine of our angle. So the cosine of our angle is going to be 8 minus 15 over the square root of 25, not plus, times the square root of 29. So this is going to be -7 over the square root of 25 times the square root of 29. And so if we just want to find the angle and not the cosine of the angle, we would take the inverse cosine of both sides. And so if I did this on Desmos and I found the inverse cosine, make sure you're in make sure you're in degrees, and then we're going to do -7, then divided by square root 25 times square root 29. And that angle is going to be 105.5 105.07 degrees. So the angle in between those two vectors would be 105.07 degrees. So again, to find the angle in between two vectors, you take the cosine of that angle is going to equal their dot product divided by the product of their magnitudes. All right, parallel and orthogonal vectors. Two vectors are parallel if they are scalar multiples of each other, meaning that if you took one vector and multiplied its components by a scalar multiple, so by 2 or 3 or 1/2, and you get a new vector, those two vectors would be parallel, meaning they would be acting in the same direction with the same angle. Two vectors are orthogonal if their dot product is 0. So if you took their dot product and you got 0, then that means that the two vectors are orthogonal. And in linear terms, that means perpendicular. Also, for parallel, they can be scalar multiples of each other, or the angle in between them is 0 or pi. So cosine theta equals, take their dot product divided by their magnitude. And if you found the angle in between them to be either 0 or pi, then the two angles are also, their two vectors are also parallel. So let's show that the two vectors are parallel. So vector v is 3i minus j, and vector w is 2i minus 2j. So you've got two ways to do it. Can you show that if I did 2 times vector v, I would get vector w? Well, 2 times vector v would be 6i minus 2j, which is vector w. So you've shown that they are scalar multiples of each other. So that means that the two vectors are parallel. To show two vectors are orthogonal, you want to show that their dot product is 0. Well, the dot product of v and w, you would take 2 times 3 plus -1 times 6. And since that is 0, those two vectors would be orthogonal since their dot product is 0. All right. How to decompose a vector into two orthogonal vectors. So we want to take one. So another way that we can solve force problems is by decomposing a vector into its two orthogonal vectors, or its two orthogonal forces. So you have the force of a box that would be pushing the box down the hill, and then you have the force that the box is exerting against the hill, and then the vector of the sum of those vectors would be the gravitational force of that box, or the weight of that box. So if we want to find vector F, or the force of that box, we can break that vector up into its two orthogonal vectors, F1 and F2. And so if v and w are two non-zero, non-orthogonal vectors, the vector projection of v onto w is given by, that vector is going to be the dot product of v and w divided by the magnitude of w squared times vector w, and that'll give us that vector v1 that we want. And then if we want that second vector v2, we would just find vector 1, and then vector 2 is going to be v minus v1. So find the vector projection of v onto w, and then we'll decompose it into vectors v1 and v2. So v1 is going to equal their dot product, so 1 times 1 plus 3 times 1 over the magnitude of vector w. Well, that would be the square root of 1 squared plus 1 squared, and then we take that magnitude and square it, and then we multiply that by vector w, so I times j. So this is going to be 4 over the square root of 2 squared times I plus j. And so that would be 2i plus 2j. And that would give me that first vector, vector 1. So up here, I've just found vector 1. And then if we want to find vector 2, well, vector 2 is going to equal the original vector, which was I plus 3j, and then minus vector 1. So vector 2 is going to equal vector minus vector 1. So minus what we just found, so 2i plus 2j. And so my second vector is going to be negative I plus j. So negative I plus j. And so that would be vector 2. All right, let's use our idea of decomposing a vector into two orthogonal vectors to look at an example of another force problem. So a wagon with two small children as occupants weigh 100 pounds and is on a hill with a grade of 20 degrees. So the angle of elevation up the hill is 20 degrees. What is the magnitude of the force that is required by their dad to keep the wagon from rolling down the hill? So how much force does the dad have to exert to just keep the wagon from moving down the hill? Well, we know that the gravitational force is going to be the weight of the children in the wagon. So that's going to be 100. And since it's in the negative direction, or the angle would be negative 270, that's going to be negative 100. So the force of gravity is going to be negative 100 pounds. And we want to find this vector v that's pulling the wagon back down the ground, because the dad's going to have to counterbalance that and do the exact same magnitude but in the opposite direction. So we're trying to find that force of that vector v. Well, we can do the decomposition of vectors. So we know that vector I would be this vector right here. So vector w is going to be the cosine of 20 degrees I plus the sine of 20 degrees j, and that's going to be our vector w. And so if we want to find vector v is going to be the dot product of those two vectors. So the force of gravity times vector w divided by the magnitude of vector w squared times vector w. So that would be what vector v will equal. So if we do this, this is going to be negative 100. So the dot product. So we have vector f is going to be negative, well, it'll be 0 and negative 100. So negative 100i, or sorry, 0i plus negative 100j. And then vector w is going to be the cosine of 20i plus the sine of 20j. And if I do their dot product, we would do cosine 20 times 0 plus sine 20 times negative 100. And so their dot product would equal sine 20. Make sure we're in degrees, and we are. So it's going to be sine 20 and then times negative 100. And so the dot product is going to be negative 34.2. So we'll put negative 34.2 and then divided by the magnitude of w squared. So the magnitude of w is going to be cosine 20 squared plus sine 20 squared, and then square rooted. So we're going to take the square root of the cosine of 20 and then squared plus the sine of 20 and then squared. And so the magnitude of that vector is going to be 1, which makes sense. And so if we square that, we just get 1. And then times vector w. So vector w was cosine 20i plus sine 20j. And so my vector v, or the pull of the kids down the hill, is going to be negative 34.2 and then cosine 20i plus sine 20j. And so the magnitude of that vector is negative 34.2. So the dad is going to need to pull with the force of 34.2 pounds in order to keep the kids in the wagon from rolling. All right, so one last idea, which is computing work. So what if instead of just what force do we need to pull an object up a hill, or what force do we need to keep an object from falling down a hill, how do we compute the work involved of actually moving an object a specific distance? So work is going to equal the magnitude of the force times the distance traveled, or it's going to equal the dot product of the magnitude of the force times the distance that it's traveling. So it's going to equal the vector F times vector AB. So vector F is the force in which you're pulling, and vector AB is going to be the distance in which you're pulling. So a girl is pulling a wagon with a force of 50 pounds. How much work is done moving the wagon 100 feet if the handle makes an angle of 30 degrees with the ground? See the figure below. So our vector F is going to be this vector right here, and she is going to pull the wagon along this vector right here, which would be your distance vector, AB, and she's going to pull it from 0 to 100. So let's find vector F first. So vector F is going to equal the magnitude, which is 50, because she's pulling with the force of 50, times the cosine of 30I plus the sine of 30J. And so this is going to be 50 times square root 3 over 2I plus 1/2 J, which would equal 25 square root 3I plus 25J. And so that's going to be vector F. And now we'll call this vector AB, or our distance vector, is going to equal, well, its distance is 100 because it's going from 0 to 100, so it'll be 100. And then we have the cosine of 0I plus the sine of 0J. And so if we did this, this would be 100 times 1I plus 0J, which would be 100I plus 0J. And now the work needed is going to be the dot product of those two vectors. So now we're going to take the dot product of those two vectors. So it's going to be 25 square root 3 times 100 plus 25 times 0. So this is going to be 2,500 square root 3, and that would be the work that the girl needs to exert in order to move that wagon a distance of 100 if she's pulling with a force of 50 pounds with an angle of the handle being 30 degrees. All right, your homework is over 9.4 and 9.5.